Alright, looks like we're back at the stream. My Twitter bots might even have worked this time. Cat seems to be in a good mood. He always takes my chair when I set up these streams, so I have to have another similar chair for myself nearby to move into position. Alright. Oh man, things have been so crazy lately. Yeah, if I was less afraid of crowds, I would probably be out there protesting right now. But instead, I'm here at home doing electronics. And streaming pictures of my delightful little kitty over the internet. I mean, as long as I can provide the internet with more cat photos, then, I think life will be a net positive. So I think mostly the goal for this stream is to do another circuit board fabrication. I have another revision of my little voltage glitching adapter board. That is not a big change from my previous revision, but fixes a couple of problems that are kind of inconvenient to patch around on a completed board. So this glitch adapter board is something I made a few streams ago to work on. It's for voltage glitching on targets that are a little bit too high speed and or have built-in voltage regulators, both of which are things that make it kind of hard to use the Chip Whisperer Lite's built-in glitching support. So whereas the built-in glitching that the Chip Whisperer Lite supports, it's set up so that you have a transistor, a MOSFET on the Chip Whisperer that when you want to inject a fault in order to, in this case, I'm trying to extract firmware, but there's lots of reasons you might want to inject a fault into a system. In this case, did I bump the wire on the camera? Anyway, in this case, you would normally with the Chip Whisperer have this MOSFET transistor located on the Chip Whisperer circuit board. I think I can actually show that on the camera here, especially if the Tuco can. Oops. Don't mind the ground clip. Maybe I'll take this moment to check out the stream health, make sure that I'm actually sending all the bits to YouTube. Looks like all the internets are happy, so anyway, hi again. Let's get this camera going. So this is my current test setup, which is basically the part that I'm about to replace. But just for the purposes of illustrating this thing that I was talking about, which it might be interesting narrative for some of you. It might also be something I end up keeping for a video voiceover later. I'm currently using, oh man, it's way behind there. Can I safely move this, kind of? It's kind of behind the microscope right now. But, can I put this there? Yeah. So that little doohickey here is the Chip Whisperer. And this is a delightful little open source hardware device made by Colin O'Flynn. And this is what I've been using lately for kind of orchestrating glitching experiments. And so in my previous voltage glitching video where I was glitching kind of a low-speed USB, well, low-speed USB has a specific meaning. It was full-speed USB, but compared to this processor, it was a much lower clock rate. So with that system, I think I could safely underclock it down to something like 4 megahertz. Whereas here, I'm limited by the Ethernet peripheral on my device under test. So I'm doing a similar voltage glitching experiment to that one, where I was, in that experiment in my previous video, I was trying to get the firmware out of a USB device over USB. Whereas here, I'm trying to get the firmware out of a much faster microcontroller that has built-in Ethernet over the Ethernet interface. Because in this particular scenario, that's the only, well, there is no intended way of getting the firmware out of these devices, and Ethernet seemed to be the first way in that I'd investigate. So in the earlier experiments with the USB chips on the Wacom tablet, there I was using this board to kind of orchestrate the entire glitching process. So it has an A to D converter, basically a simple oscilloscope, and it doesn't actually have to sample as fast as a standalone oscilloscope would, because it can synchronize the sampling with the clock that it's either generating or recovering for the device under test. So the idea there is that you'd have a predictable, you'd have like a locked sampling waveform driving the actual A to D converters, so that every time you sample, it's at a predictable point within a clock cycle in the microcontroller that you're trying to target. So you can get away with a much less expensive A to D converter. So this was designed to be kind of an entry-level glitching platform. But for those slower processors, the capture worked really well. And I was using it for a while in tandem with my new oscilloscope here. And it wasn't really giving me any extra information, but it was at least kind of confirming what I was seeing on the scope and letting me kind of cross-check the stuff that I'd seen earlier via the chip whisperer against much higher bandwidth traces that I'm seeing now on the new scope. So so that was helpful for a bit, but I'll go through a little more detail on some of the recent debugging, but I ended up disconnecting it mostly because of some issues I was having with oscillation. Well, I don't know if I want to call them oscillations. I think what was happening was some combination of kind of badly terminated cabling attached to the core voltage rail here, combined with the load dropout voltage regulator in the chip that's actually trying to power the core rail. I think that basically I was adding some reactance to that that voltage regulator that was causing it to oscillate. And I mean, an oscillating regulator is a thing that I've known about, and I've been trying to track that down. But I assumed it was due to some of the wiring on the kind of low impedance part of the circuit, where I'm actually, over here, where I've actually got a glitching transistor board soldered really as close to the processor as I can, and I'm working with really low impedance signals. I ended up tracing some of those oscillations, the ones around, between like 7 and 12 megahertz. Those ended up disappearing when I removed a bunch of the cabling from those two B and C connectors, one of which was leading to my O-scope and one leading to the chip whisperer. So I think that was some combination of bad cable termination and putting, a load on that regulator that caused it to be unstable. But instead, so instead of having a 50 ohm probe on that, I've gone back to using high impedance probes. And so my current probing strategy, you can kind of see there in front, I've got these, so these are passive 700 megahertz rated probes. They're the ones that came with the scope. And the end of the probe is a nice, it's like a spring-loaded pogo pin kind of connection. So it's actually pretty good at, if you put it under any kind of pressure, it'll kind of make a good connection, gold-plated and all that. And then outside, I've got these, those are those spring clips also that came with the probe, which actually make a great ground connection. And in this apparatus, I have these, is that maybe where I should be focusing? Yeah, so if you look right where I'm focusing now, I mean, I'm going to be disassembling this, so I don't actually need this in one piece right now, but, so you can kind of see what's going on. It's, It's giving me a really good signal on the O-scope, but it's mechanically really dodgy, which is a big part of why I'm building a new board for this now. So it happens that, so these are female headers, like the nicer machined pin style, not the kind that are just like stamped metal. And I think they're pulled out of an IC socket, so I had some like fancy IC sockets sitting in a drawer, and I took them apart and just like cut the plastic off. And then it turns out that, you know, with the thicknesses of the wires here, the grounding wire on the scope actually makes really nice contact in that socket. So the way I've been putting these in is basically sticking the ground wire in there and then using that to provide some mechanical tension to give good contact on the probe point. So I've been liking this strategy. I just want a board that actually has holes for these connectors, because this is just super dodgy having them just like tack soldered onto the surface like that. Let's see. Anyway, I'm getting a little bit ahead of myself. I was trying to explain why the chip whisperer itself isn't really doing as much in this experiment as it was in the previous experiment. So there's the chip whisperer again. And normally I would be using that left connector labeled measure as an oscilloscope. I probably still could be doing that. I just took that off at this point because I don't have like a nice high impedance probe for this that I trust. So I took this off as, you know, I think it was the other cable. It was like the longer cable going to my O-scope. I think that might have been a 75 ohm coax instead of 50 ohm, and I terminated it for 50 ohm. So I think that might have contributed to the problem. But just because I didn't really need this anymore either, I took it off to keep it from influencing the circuit. And then that connector on the right labeled glitch is normally what you would use to actually you know, sync that current pulse into the device you're trying to inject a fault into. But I was having trouble with basically this is a fairly high capacitance MOSFET they had on there, and it was being driven directly by the FPGA, which can only drive a couple of milliamps really. So it just wasn't switching on and off fast enough to insert glitches that seemed to affect, you know, a chip that's designed to operate at 120 megahertz. So in order to get faster glitch edges, I forget what they were before I started. I think they were in the neighborhood of, I want to say they were like over 50 nanoseconds, but I've probably got screenshots of scope traces from back then that I could actually check. But with the current setup, I'm getting glitch edges that are, I think, like 5 nanoseconds or something in that neighborhood, which seems to be working much better. Anyway, so I ended up modifying this by taking off the MOSFET and actually just tapping off the drive signal, and that's on the kind of purple and gray wires there in the front. So at this point, the chip whisperer, it's actually orchestrating the experiments. So I'm using its software to start the experiment. It's got a GPIO that's actually resetting the target board. I think that's the orange wire. Yeah, the orange wire is the reset GPIO. The white wire, or the yellow wire, is a trigger signal coming in from the device under test. And then the black and white wires, that's the clock it's generating. So yeah, the chip whisperer at this point is mostly, it's running the experiments, it's timing the actual glitch using the trigger that comes in from the board, and then it kind of waits a programmable amount that I can also sweep over a range of values in order to look for a good spot. And then it's actually generating a pulse for that MOSFET that's now going over the purple wires. But then all of that is also synchronized with the clock that it's generating. And this is another complication that I've mentioned in some of the earlier videos, but the clock that I'm actually putting into the device under test isn't the same as the core processor clock that I really want everything to be synchronized with. So that's why I have that clock going into another FPGA here that's kind of trying to do the inverse of the clock synthesis that's going on in the target, but I'm skeptical about how well that's working, because I think that's going to introduce a lot of kind of phase unpredictability. So I think that's probably what's contributing to a lot of my my trouble in kind of isolating glitch parameters that work reliably. So there's the FPGA, that lattice ice stick there. The yellow board just has a voltage regulator and the transistor that drives the reset, and it's bringing together some of the trigger signals. But then this is the glitch adapter board that I made on the earlier stream. That this is what I want to be remaking tonight. So this one, so I designed this as kind of my first attempt at using like real high-speed MOSFET drivers. So these are basically just like the best fast MOSFET drivers that DigiKey actually had in stock. And I think they're rated at something like 5 amps of peak current during the actual the gate transition. And so they've actually been performing really nicely. They've been giving me good edges. They've been driving the MOSFETs well. I have 3 of them on this board. It sort of looks like a classic totem pole driver where you have N-channel MOSFET on the bottom that can pull the load low. Then you have an N-channel MOSFET on the top that can pull the load high. And then you have to generate a gate drive voltage that's actually above that high rail to turn on that top N-channel MOSFET. It's sort of like that, except I have 3 stages. Well, I did it in this board. I won't go into the schematic right now because it doesn't matter too much, and I did in a previous stream. But in that version, there was both the low kind of side of that to just short out the output. That's what I was using to introduce low-level glitches where it would momentarily go to ground. Then there was another MOSFET that was normally connected, and that would connect a bank of capacitors to the to the V-core rail in order to stabilize its voltage regulator, because without any capacitance, it'll oscillate. And so I wanted to balance, having some capacitance there to prevent the oscillation, but to take out as much of it as possible during the glitch. So that's why I had that middle MOSFET. Then I also had another MOSFET on here, which I didn't really end up using, that was designed for doing higher voltage glitching. And that, I'd still like to avoid glitching with higher voltages if I can avoid it, or if I can, because that's a lot more likely to damage the device under test. So I've elected to remove that from the next version of this circuit board because it looks like I don't need it. I think I can get what I need from glitching to 0 volts instead of having to do high voltage glitches. And so that was just another N-channel MOSFET connecting the target voltage to another small bank of capacitors that, I connected to a power supply or a battery or something. So besides the mechanical problem I mentioned where, I kind of at the last minute changed the probing strategy and ended up putting these things in that are electrically nice but mechanically awful. I guess you could say the same thing about the connection to the board. Since originally I had this, oh man, you can barely see that with this camera angle. Yeah, so you can see that 2-pin header there, gobbed in hot snot. In this case, I used the hot glue instead of the epoxy because this is a lot easier to take off. You can just use, 99% isopropyl alcohol, and this stuff just comes right off. So since I knew this fixture was temporary, I wanted to glue it in a temporary way. So in this case, you can see that connection to the chip is really critical. I mentioned this some on some earlier streams, but as I'd been having trouble with the cable that I put in there. It was improvised and really bad. I'm trying to see if it's here, but once I realized I was having problems that were related to that interconnect, then I went and read up a whole bunch on all the bits of E&M theory that I've forgotten since the last time I looked at something like this, and realized how bad that design was. And so I think that cable just had too high an impedance, and there was probably just too much of it. And so I was getting these oscillations that I would measure when I had the probe right on the processor, that then when I put the probe on the circuit board that was like 1.5 inches away, I wouldn't see those oscillations anymore. So I think it was some combination of the conductors and the cable being farther apart than they should have been, and it possibly being lossier than it should have been, especially at high frequencies. I made something out of like random copper tape I had around, and it could be that wasn't high purity copper, and that I actually wanted something that was plated. And so anyway, I was reading up on alternative cables for that kind of thing, like really low impedance signals, but I think instead I just want to get this as close as I can get it to the chip. So this electrically looks a lot nicer, but mechanically it's just terrible. So I was thinking about maybe fabricating a version of this board on a flex PCB, but I think I want a ground plane, and I can't really make, I don't have like double-sided Pyrolux here, so I think I'd rather just try making a plain old double-sided FR1 board that I can make on the mill, and then just try to put it really physically close, kind of like I am now, but hopefully less inconveniently. This is super inconvenient the way it is right now. I've tried to stabilize it as much as I can, but it's already putting some bad stress on the circuit board, and it's been hard to add and remove capacitors and that sort of thing. All right, I think the next thing I wanted to do is to try to summarize some of the results I've had so far. I have some video clips from the last few experiments really sped up. Yeah, let's get this slightly out of the way. Go back to Servo AF. Happy cat. All right. Although I think I'm probably going to end up having to take that off the screen in a sec because I need the full screen for the videos. Okay, let's see. How far back do we need to go? I think it's got to like pull in a bunch of stuff from this network share. Okay. So these are mostly time-lapse videos that I recorded from experiments here. I've also got some cute ones like this. Let's see. More cat. Where's the first experiment? Is this the first one? All right, let's let this get to something good, and then I'll explain what's going on. Is this one too early to get to something good? Ooh, there we go. Whoops. Let's open this for real. All right, so these, I mean, they're clearly time lapses. So this is basically the same test setup, a somewhat earlier version of it. So up here in the corner, there's the DSLR viewing the test setup. That's the same circuit board, but I had it connected with that kind of, unexpectedly bad copper foil cable that I made. And I guess another thing that changed here, so I didn't end up using that high voltage glitching circuit at all. I also ended up kind of changing the voltage almost right away. So I originally designed this to drive the MOSFETs off of 5 volts, and I pretty quickly discovered that the edge rate that I was getting was kind of mediocre, and so then I cranked up the voltage to the maximum that these drivers can handle, which is 12.5. So that's what led to the rest of this kind of power stuff over here, where I'm just piping in 12.5 volts from a bench supply, and then I just have a local couple of regulators to give me 5 and 3.3 for everything else. And then the 12.5 goes right to the MOSFET drivers. So this is the machine running the Chip Whisperer software, and so it's just repeatedly changing the parameters for the glitching. I forget which of these is which right now, but basically these 4 parameters are coarse and fine adjust for both the period and phase of the glitch pulses, where we're actually shorting out the power of the microcontroller at a predictable point in relation to its clock waveform to try to trigger different effects in the microcontroller to get different glitches. And so it's also orchestrating the experiment by periodically, at the beginning of each experiment, it resets the target using a transistor over here and a GPIO on the chip whisperer. And then it sends an HTTP GET over this this Ethernet interface that I've talked about before that's kind of an underclocked weird thing. So it's just sending an HTTP GET to initiate the experiment, and then some code on this target microcontroller, which would normally just be the kind of victim device that we're trying to investigate. That is actually just running, it's running kind of some example code that's similar to what the actual industrial devices running this processor might use, but I've instrumented it with a bunch of debugging stuff that can help out. And so in this case, I'm not even returning a file from the file system in Flash. I just have it running this experiment that's basically just a big bullseye for glitches, where it sits in a loop, incrementing a counter and loading and storing values into memory. And it gives me a total which, if everything went normally and no glitches were involved, the total should always be 1,000. And so you can see over here, well, let's go back a bit, because this is actually a glitch that succeeded. Let's try to find one that, oh, this is really sensitive. Oh, this is actually this is such fertile ground here. Maybe I should go to the full-length version of this video. Which one is this? Oh, I don't know if I have the full-length version of this. Oh, yes, I do. It's like 100 gigabytes. This is going to try to play sound, isn't it? I should make sure I can mute that, because it's going to be annoying otherwise. Oh, why is this opening in QuickTime? Do I not have VLC on this machine? Pardon me while I complain about computers. Let's change that default. Yes, that's what I wanted to do anyway. Thank you. This is a read-only share on the other computer that's doing the recordings. Sure. Okay, this is the file I want. Turn off all the background audio. A 100 gigabytes. Oh yeah, real time. Okay, so I think it was around here. Cool. This was late at night when I had this experiment running. So there are still some problems. I've temporarily put aside the problem where just like about half the time it doesn't respond over Ethernet, even in the slightest, which is super annoying, and it slows down the tests a lot. But I figured I would take a break from that problem since I was a little bit out of ideas at that point, which has probably been a good decision, since I'll come back to that problem soon and maybe have some fresh ideas. And in the meantime, I've found some different problems. So you can see it kind of slowly plodding along. The red lines are when it sends the HTTP request and just doesn't get an answer. The kind of plain ones, the white background, those are the expected result. And so when you get one of those, we should get a scope trigger, like there. Let me pause that. So that just operated as expected, even though we gave it a glitch. This is the chip whisperer's view of the glitch through its measurement port. This red trace on the oscope is the same signal, but at a much different time scale. This was before I had solved the lower frequency oscillations, so that's what you can see here. I think that's the voltage regulator and my cabling fighting each other. And then here's the glitch itself. And this bottom window here is just a zoomed in view of this little sliver here where the glitch is happening. So basically the glitch happens here But down here on the bottom, you can see this is some debug code in this glitch target that's just every time it goes through the loop where it increments this counter, it's also dumping that value to a little 6-bit general purpose I/O bus. So that's what these pins over here are from the oscilloscope. There's a little parallel bus where every time it goes through the loop, I just kind of log that value so the scope can see exactly when the loop is happening. So in this case, we can see that the glitch was delivered here. These little pulses here that are kind of below my current zoom level on D9, those are actually the drive pulses coming into the glitch amplifier here. Those are coming right out of the chip whisperer. And at this time scale, we can't really see the detail there, but we will shortly. But we can see here that the glitch happened, but the processor just kept running. This trace here, the little sawtooth wave, this is actually just a graphed representation of these numbers on the parallel port. So this sawtooth just means that the lower 6 bits of the counter are incrementing and then wrapping around, and incrementing and wrapping around. So that's exactly what we would expect if the loop is running without significant intervention. So that happens for a while, then the timer runs out, and then it just kind of sits here at the last value. And then there's some debugging that occurs when the Ethernet interrupt happens. So that changes the value a couple of times as we actually send the responses. And in this trace, the blue was going to be a packet coming in from the Raspberry Pi to this device under test, so that's kind of way off the left edge of this trace. And then the green is Ethernet going the opposite direction, so this is the device under test transmitting the response, which is actually what you see here, the HTTP 200 and the body here with the 1000 response. So that's kind of a background on what this experiment is doing and what it would normally look like. But shortly we're going to start to see some glitches actually happening. So let's see how much we need to speed this up. Oh, that was one. Pause. Okay, neat. So that's interesting. So I ended up simplifying this glitch experiment a lot. Originally, I had this running kind of much longer loops, and I was triggering a glitch, in the middle of a much longer process. Here, it seems to always fail in, there's a relatively small number of failures I've been seeing. So this one is one where as soon as the glitch is delivered, which always seems to happen at the same iteration count, it ends up breaking out of the loop. That in itself is pretty interesting because I don't think it would be doing this via actually diverting control flow, because for it to break out of this loop but still correctly form the response, that's like the same C function, so it would have to have a very targeted way of doing that. It seems more likely that either the glitch is causing a comparison to return the wrong result, or a jump not to take place when the jump should take place. So it's effectively skipping just a small number of instructions ahead. Or the glitch could be modifying some register values such that the comparison in the loop immediately fails. So it's hard to tell exactly what's going on at this time scale, but we can start to see that this particular kind of glitch is something that we might want to try to make reproducible. So one thing I want to pay attention to here, for example, is if we can get a better idea of where that break is actually happening. So it's somewhere after here. So this loop from the end, this thing between 13 and 14 to between 14 and 15, this loop happens normally. And so the glitch that we're delivering is this bank of pulses right here, and we can already see the power supply start to swing wildly. But despite that, it still crosses into the 15 at the time we'd expect. But then right after here, something goes wrong, and it actually ends up exiting the loop. So, that could mean a bunch of things. It could mean that this is causing changes to the registers, and the actual control flow change happens later. But it seems more likely that maybe this is telling us something about which of these electrical artifacts are actually responsible for the glitch. so that maybe it isn't this initial pulse, but maybe the positive swing when the power supply kind of inductively snaps back upwards after we release it. So that's the kind of stuff that I want to try to isolate with these experiments. I want to first try to see what changes in the glitch pulse structure would change, how that would affect the timing. But then I would also want to actually slide these pulses in relation to the experiment and see what the thresholds are for it actually causing loop breaks. So let's go a little farther in this trace and see what happens. Maybe go back to the high-speed version. Yeah, so here you can kind of see this is kind of why I wanted to do a time lapse, because these experiments are still so slow, but this is, I think, an easier way to see some of the patterns that emerge. So it's a little off the edge, but this is sweeping through parameters. I think I actually changed the setup to be a little better here. Yeah, so now you can see it sweeping through parameters, and oh yeah, that's interesting. Oh, this is something I might want to take a look at, slightly slowed down. So here, yeah, I still didn't really have enough resolution to see the actual glitch pulses on the scope here. Anyway, there's a lot going on here, and so I think during part of this I was looking to just collect some data to try to make some interesting correlations between the timing of the glitch pulses I was delivering and when I would actually see the processor's behavior change. That was part of it, but then I also kind of went into some tangents on trying to just stabilize this whole environment, because, like, for example, this oscillation is something I really don't want, and so I went into some rabbit holes, kind of trying to experiment with smoothing that out a bit. That's interesting. I don't think these pulses were actually supposed to be there. Oh yeah, no, that's right. This is intentional. I just hadn't actually seen this. This is the pulse that actually detects a successful glitch. That's the one I added in the debug code. So you can see most of these are either successful at 1,000, or they're detected as glitches at 469 by this loop breakout mechanism. But electrically, there's still way more junk here than signal that we actually want to try reproducing. So, like, it's starting to be clear that the loop break is happening kind of around this inductive swing right here. But yeah, I think we want to take a closer look at what's going on. So I think this test was like the first long one that I ran, and I was getting all these useful results, but the actual test setup was kind of suboptimal. I wasn't zoomed in enough to see the details on the glitches, and I was kind of preoccupied with this oscillation here, but now I'm pretty sure that was just that cable/regulator problem. So I wasn't really focusing on the right details during this experiment, despite having a lot of green in the outputs. So let's skip ahead a bit. I think I misunderstood how the screensaver on the scope worked. I thought that maybe the screensaver was reset by the scope triggering, but I guess it's just reset by front panel interactions. So of course it went into screensaver mode. I disabled that. But it looks like a lot of these were pretty similar. This didn't really end up with a lot of different glitches, I mean, if this is relatively reliably giving me a loop break, then it's a good sign that I'm on the right track. But I want to understand a little better how to make this environment more stable, because this is still the kind of unreliability that would get really annoying when I try to take this same experiment and port it to a processor where I have less debugging opportunities. Oh. Morning in the lab. That was a nice ear fleck there. Oh, some good cloud motion down there. Oh, it's still super zoomed out here. What was I changing? Same parameters, the fine and coarse duty cycle and phase adjust. So it looks like here I'm getting a lot of the same oscillation. I'm triggering loop breaks. This time it's happening in that 14, so it could be a little earlier, but it's a little hard to tell. Interesting. This isn't really giving me anything new, though. I think I want the next video file. Let's try U. Oh, is this one just cat related, or is this electronics also? Oh, that's so cute. I think I shared a really sped up version of this on Twitter. Anyway, where's the next experiment? Ah, this is nicer. Hello, NAS. You can do it. Why is this not opening in VLC? I guess that's the different extension. Probably MOV before, and this is MP4. Alright, so this time I was looking close enough that we can actually see the individual pulses. And I think you can also see here that... Oh, so what was my setup here? This was still using the long cable. And so this time... So this is DC coupled. This is the power rail for the processor. So normally it's hovering here at like 1.2 volts. Ground is way down there. And right here, the first glitch pulse happens. So this D9 is just a digital version of the signal coming in from the chip whisperer. Or rather, it's the chip whisperer signal, and it's like on one of the digital scope inputs. I think it's this connector right here that you can see in the DSLR. So, and if you're wondering about the camera on the empty foof, I think I was hoping that Tuco would hang out there. I was like making a spot that I figured he would find comfortable in the expectation that he would perhaps camp out there. I don't know if he actually did. I guess we'll find out later. So this is the first thing that happens. This is the trigger right from the chip whisperer before it's gone through any of the propagation delay in this circuitry. And then I think this was my early attempt at probing the MOSFET gate there. But that looks really precarious. That must be the MOSFET gate, though, because that scale is 10 volts per division, and the MOSFET's the only thing running at that high of voltage here. So, and what is my time scale? This is 50 nanoseconds. So we're not zoomed in much, but you can get some idea of how steep that edge is. I mean, again, this is 50 nanoseconds, but that edge should be in the single-digit nanoseconds. So as soon as that happens, you can start to see some stuff happening on the power rails here, but it isn't really the stuff that I would have wanted. Because, you know, ideally, everything ideal, this would just go straight down to 0 here, and then return kind of gently up to its normal voltage, or, you know, relatively gently. But instead, what you're seeing here is that I'm getting a lot of oscillation in the power rails. So I think this was something that ended up going away when I simplified the cabling situation. So I think what was going on here was probably, you know, you can see this pulse down here, basically. I think that's the same, that's a comparable frequency at least. So this high frequency ringing is probably basically this impulse kind of hitting the power supply like a tuning fork and setting it oscillating. But then you're also seeing this much lower frequency oscillation, which I think was that cable and regulator oscillation that I was seeing earlier. So let's see how this continues. So again, this is like, parts of this are what we want, but then parts of this are just like junk that I would really rather not have to look at. So let's clean up the experiment so we have less unpredictable mess and more stuff that we can actually control. And that's kind of been my strategy in trying to make these glitches more reproducible. I think there's a lot of stuff working against reproducibility right now. There's this electrical environment that I've been working on. There's the clock phase stuff that I mentioned but haven't really worked on yet. So anyway, let's see where this goes. So this is looking at different timings. The chip whisper glitch generator is really weird. I think I might need to go read the source code to understand how its FPGA is actually generating these glitches, because the parameters that I'm changing are supposed to be basically a pulse width and like a phase offset. But, well, okay, so here I seeked back a little too far, but this will show a different point. When we're back here, this is a big train of pulses, and so this is kind of a shotgun approach. This is like, I have no idea what parameters are going to work, and I don't know what offset in time is going to work, but if I just make a bunch of glitches, then it's more likely that one of them will give me an interesting result, and then once I've produced some kind of result, I can narrow down what made that interesting and then send fewer pulses. So I think that's this kind of experiment. Then, let's see. Then I was trying to just see how far I would get with much narrower pulses. And so here, so this pulse, what is this? This is like 20 nanoseconds or so. Pulse width, not edge rate. But, like this looks fine. But then, I'm changing the parameters here, and I can get these really, really skinny pulses that aren't even fast enough for the MOSFET driver to react to. And then, I haven't caught it on one, but you can occasionally see where it leaves the trigger on. Like, that's got to be a bug. And I actually had to protect against that in hardware. Like, my glitch board has a little RC filter just to keep these kinds of things from lasting forever. So yeah, I mean, the chip whisperer is still useful for orchestrating these experiments right now, but the timing here is starting to become a weak point, so I've been looking at other options. One thing I've been interested in trying out is this Arctic, ARTIQ. It's like an open source package for doing precise timing for quantum computing experiments. So that might actually be something I can run once I ordered a Papilio board, because that's one of the FPGAs they support. So I'll actually get a chance to try that out here soon. So yeah, I mean, I was hoping this experiment would give me a good idea of the effects of these different pulse widths and would help me kind of calibrate which of these were most effective. But I think really this was just overwhelmed by this terrible oscillation that I'm getting, and how I think this is related to loss in the cable. That so this MOSFET is physically really close to the processor, but still separated by a cable, which I now have some suspicions of. But then this red trace is on the other end of a long, nominally 50 ohm transmission line that I also believe was kind of suspect. So I think what might have been happening is the MOSFET actually pulls pretty hard, and I get a nice low impedance pulse, but then I don't actually see much of that on the processor, and then I think I see even less of it at the end of this transmission line, because I think that cable was actually responsible for this lower frequency signal. So anyway, let's skip ahead. Oh, here, so you just saw me change the probing setup. And so now the yellow is what we were seeing before for the MOSFET that's actually kind of trying to clamp this down to ground. But the blue is one of the other MOSFETs I mentioned, the one that is normally connected and tries to connect those stabilizing capacitors. So I was having a lot of problems with that, which you can't see in this experiment, but that'll become more evident later. Oh yeah, and the green trace, I think this is the capacitor bank that the blue MOSFET here is supposed to be connecting. And so that is supposed to be just rock solid if I can. And I had a really hard time stabilizing this, because in effect what was happening, well, actually, I think this became more complicated, or was more complicated than I expected. But so if you look closely at what's going on here, so the first thing that happens, we get this short pulse on D9, and this is coming from the chip whisperer. This and this actually is not fast enough for the yellow MOSFET driver to react to. So these MOSFET drivers happen to be balanced nicely, so there's some dead time where it's a little faster at pulling the MOSFET low than it is at pulling it high. So when these two drivers are asked to change their signals at the same time, in effect, one turns off, then there's a gap of, in this case, it looks like 5 nanoseconds or so, and then the other one turns on. So that's really good because that doesn't end up shorting out the capacitor bank. So we should pretty solidly disconnect the capacitor bank and then short out the processor's V-core right here. But what's actually happening is as soon as this signal comes in, there's a little bit of a propagation delay for the MOSFET driver, and then the MOSFET driver throws this blue waveform down really hard. And so these are actually pretty high magnitude. You can see up here, this is 10 volts per division, whereas the other traces are 100 millivolts and approximately 100 millivolts. So I think a lot of stuff is going on here. I think some of this was, so I think this lower frequency stuff might have been an oscillation between the capacitor bank and the voltage regulator once it was reconnected. But I think this higher frequency stuff actually could be that MOSFET driver itself oscillating. I thought there could be a bunch of different causes for this, but I think right now I'm pretty sure that is the high side driver, so like the N-channel MOSFET that's connecting the capacitor bank with this blue trace. I think it's that transistor oscillating at a much higher frequency. So I've got better traces for that a little bit later, because that was one of the problems that at this point was really throwing me for a loop, and then I think later I got some better illustration of what was going on. So yeah, here you can see that noise on the capacitor bank kind of changing in response to the pulse widths. And yeah, it looks like, I'm kind of coupling a big impulse of some sort through that circuit into the capacitor bank, and then that kind of sets off an oscillation. But let's go forward to where we have better traces of what's going on. I don't think this is it, but ooh, yeah. So this is just kind of a closer kind of time-lapse look at the pulse widths changing. So I think here you can actually start to see what's going on. You see these oscillations here where the green and the blue traces were kind of in lockstep with each other. I think that's, so in this case, the green trace is the source of that same MOSFET, where the blue trace is the gate. And so you can see this kind of bounce. Oh, that's interesting. So it's almost like this very fast edge rate causes this fast edge to appear at the source also. Like that edge is just being coupled through the parasitic capacitance somewhere, possibly through the MOSFET. And so, because it looks like that's happening at pretty much the exact same time. But then once that happens, that starts the MOSFET into a self-oscillation. And it's probably hard to see at this voltage scale, and I don't think I understand the order of operations in that oscillation well enough to explain it. But the best advice that I've seen for damping this kind of oscillation is to add a bit of resistance on the gate to just slow down this edge some to prevent it from from starting this kind of oscillation and to damp it if it happens. So that's one of the other reasons that I want to spin a new board. The current board doesn't really have room for that resistor, and I probably should have left that, but there's a lot about this board that was very prototypey, and so it makes sense to spin another one at this point, I think. So that's what I think we should get into doing pretty shortly, is to finalize that design and start cutting it. But I think what I want to try to do is have either no additional resistor or a very small one on the yellow transistor here. Because that one, I actually do want this to have a pretty sharp edge, since that's actually intended to introduce glitches in the circuitry. But the blue one, I'm kind of just trying to make room for the glitch, so I don't want that to pollute the capacitor bank with all this oscillation, especially not this like amplified oscillation with the MOSFET. So that I really want to slow down the edges a bit. I don't think to the point where I don't want this nice fast MOSFET driver at all, but maybe for consistency use the same driver for both MOSFETs, but have some resistance to slow down this one. Let's see if there's anything else interesting in this video. I think this is just more of the same tuning settings. And it's really hard to see any correlation between, well, I guess in this particular test setup I didn't get a lot of successy glitches. So I had a much better view of what was going on, but I didn't see a lot of green in this one. Can we run this one faster? Oh wait, was that green? I thought I just saw that out of the corner of my eye. I wasn't really looking at the screen because I was about to go back. Yeah. What's going on there? Maybe I can go find this in the, oh geez, do I have the full speed version of this? I'm sure that file's enormous. That's 5.8 something. Really would have been nice to have that number in frame. Oh yeah, this one's only 70 gigabytes. Sure. Hard disks are cheap, right? I don't know how long I'll keep those full files for. I don't think I need them. Are you opening? Oh yeah, that's full speed. Me in my pajamas and everything. Oh, maybe I'll speed this up in VLC. I mean, these probably aren't going to be super... Oh, there's one. These are probably going to be similar to what we saw before, but just maybe I can get more detail on it. This is much easier to do in video editing software. Well, maybe I'm not going to bother with that. That's too annoying. How about this one? Is this one any good? Whoa, that one looks kind of trippy. Maybe some compression issues there. Glitchy scope is kind of interesting. Oh, this is still with the old cable setup. think the next results that are worth looking at are after I change the cable setup. Was that this one? Yeah, so this, I remounted the board directly. So that made a huge difference. So I'm no longer getting those crazy oscillations in the red trace anymore. Man, VLC is having a hard time with this codec. This is like more vaporwave than I intended it to be. Yeah, so anyway, where is the interesting part of this? I can't not hear vaporwave in my head while I'm trying. Okay, maybe maybe it's just having trouble playing the slow-mo version, or the speeded up version. You can do it, VLC. Okay. Oh, maybe VLC was having trouble because I think I also had VLC set to speed up. Oh. Oh yeah, maybe VLC just has some keyframe bug related to trying to speed up this video. Yay, real-time debugging. Okay, that's looking better. So we'll take a look at the successes in just a sec, but you can already see that the signal is like way cleaner. So, and we're looking at this at a much closer time scale. So now this is like 20 nanoseconds per division. These are individual glitch pulses, we're not just looking at like a glob of pulses. And now you can see that we're actually getting, quite a lot of response on this core voltage rail for each individual glitch pulse. So let's see, on the first pulse it doesn't actually get all the way down to ground, but there's this big rebound when... Oh, okay, actually, that's interesting. This is not what I expected. So I was looking for a... Well, okay, just to recap a bit. So green here is the capacitor bank again, and red is the... red is as close as I can get to the actual core voltage on the processor. So it's pretty stable before we do anything. Then we take off, or we release this connection between the capacitor bank and the vCore rail. Some of the oscillation starts up. I think I might have already put a little bit of resistance in at this point to try to damp that, but there's still a good bit of oscillation. And so that's this going low. Then the blue trace going high is the other MOSFET trying to clamp this to ground. And so that's also trying to pull this low. But it doesn't actually get all the way to ground. It just kind of starts all this oscillation happening. Then this big impulse here, I think it looks like what's going on here is this seems to be happening in response to the yellow MOSFET's gate going high. So this is the one that normally connects to the capacitor bank. So, and it also seems to coincide with this peak here on the capacitor bank. So it might just be that we're seeing this, like this is oscillation from the capacitors being coupled back into the power supply rail. But again, the voltage scales on this are pretty weird. Like these are both supposed to be the same scale, and this is a much bigger peak than we're seeing here. So that still has me a bit confused. Let's go forward. Oh yeah, lots of oscillation there. It's also weird. Let me stop this for a sec. It's also weird here that um, the oscillation I'm getting here on that capacitor bank seems to be happening before my MOSFET gates change state at all. So, I don't know. This seems like, I mean, either it's something unrelated or it's something caused by the circuit that's actually processing this pulse right here coming in on D9. So it does seem like that first big edge here lines up with that. But it's been hard to debug this particular board for a lot of reasons. Partly, like, as you can see in the camera here, the probing situation is kind of nuts and it's super fragile. It also just doesn't have the best routing and grounding that it could have. So part of what I wanted to do was to design the board with a bit more attention to keeping the paths that actually turned out to be critical, both small and easy to debug. And I got all the signals on the front layer, so I can just use the back entirely for ground, which I also imagine should help. At least help the problems be simpler, so that I can debug them more easily. So, I mean, the main thing that I don't like about this state of affairs that we're seeing right now is just that all the junk that we're coupling onto the processor via oscillations in this capacitor bank, like, that's at least as significant as the glitch that we're intentionally injecting. So that seems to be, like, I would not expect to be able to get a predictable, reproducible glitch given that. So given that my glitches haven't been reproducible, this is something that I'm strongly suspicious of. Definitely different frequency components going on here too. Like, I don't know what of this is, like, I think the really high frequency stuff at the beginning here is the transistor oscillating. I think some of this might be inductance and capacitance in the board. I'm not really sure. I haven't been able to track it down at that level of detail. Oh, I think right here the Ethernet interface got stuck, and so all the experiments ended up failing until I rebooted it. Oh, we could watch the sun come up, though, because that's kind of pretty. Is it coming? That's close enough. It's morning in scanlime country. Maybe I'll try to catch up on chat slightly while I'm also drinking my beer. Oh man, look at them sunrise. I'm trying to parse a comment from Ryan, who says, at this point, if you're making a new PCB, might it just be as easy to redesign the red PCB? Oh, the one, the device under test board. Maybe. That's a good question. Yes and no. That's a good question. So, I mean, the essence of this is, should I should I be designing kind of an adapter for doing glitches, or should I be designing kind of a complete system for doing the experiment that I want? And I can see arguments for both of those. My current thinking has been that I'd rather have a little portable tool that I can just solder onto whatever I want to glitch. But that definitely causes challenges with like mounting and signal integrity. So yeah, I mean, the flip side of this is that basically the same arguments have to apply both to this kind of test scenario and to the like real world devices that I want to get firmware off of. So with those, there's also the same question where, you know, I could try to modify that PCB, or I could just try to make a clone of their circuit board basically that's stripped down to just the bare minimum stuff that I need. And so far, it seemed easier to modify that board than to make one from scratch, but I definitely feel like I've been on the fence with that lately, so kind of hard to say. I think right now this board is simple enough that, well, the board is simple enough, and the like red development board is kind of relatively development friendly, so I'm just going to keep gluing stuff to it. I guess I woke up and restarted the experiment, and what is this doing? I guess I'm checking email or something. Oh, yeah. Okay, so this time, let me go back slightly. So this time I'm keeping the timing of the glitch constant, since I've got plenty of video about that at this point. And so I'm generating this relatively small train of glitches. Ooh, you see that? What's that thing? The yellow is coming and going. Whoa. Sorry, that I just noticed that. It's right here where my... what is that? Huh. That also might be some kind of weird signal integrity problem. So, I mean, what is that? This is 50 millivolts, but it's all over the place. It's hard to tell actually how big that voltage swing is. Anyway, that, I wasn't expecting that. I don't think that's the chip whisperer's fault, though, because this waveform down here looks pretty nice, and that's what we're getting from the chip whisperer. So I think this might be some noise on my glitching board. So something in the buffer that sits between the chip whisperer and the MOSFET drivers, so that's kind of crazy. So yeah, I definitely want better grounding, better capacitors close to the MOSFET drivers, because I think they could be introducing current transients. This was also an offset sweep. Oh, how did I break it? Oh, yeah. So here I'm looking at the really early days of that oscillation. I think this was around 500 megahertz. So and it looks like things are happening at around the same time, but I think the first thing that happens is this MOSFET gate. Well, the first thing that happens is that this. Bleh. The first thing that happens is we get a low edge on the signal from the chip whisperer, which is. I mean, in this case, this is telling us to kind of disconnect the glitch transistor. That's interesting. Why am I looking at a low edge? Is there actually a rising edge right before that? It's a little hard to tell when I'm this zoomed in. Oh yeah, that was just a little pulse. Okay, so a little pulse comes in on D9, and it's enough to briefly disconnect the blue MOSFET. I'm curious if this oscillation up here is at all related to this pulse coming in. you know, maybe, because there's some signals I wasn't monitoring that go in between this D9 right here and the blue and yellow analog traces, and so I'm wondering if maybe those are swinging around wildly and causing this, but I don't care quite as much about that. The really nasty stuff is up here when the blue trace also starts oscillating, because this means that now my MOSFET gate is oscillating and it's amplifying the oscillations. So that's what I was trying to get a closer look at. Yeah, so it looks like this happens first, and then oh, that's interesting. That's my 180-degree phase shift. So I think, yeah, the blue, red, and green traces on here are all on the same transistor. So I think that was what led me to just decide, yep, this is probably the transistor oscillating. Yeah, so, okay, let's see if I have any footage from after I added that resistor. I think here I was just running. Did I not have the camera on? All right, are we out of useful material here? Yeah, there's one more. Let's see if this is interesting. Oh, this is with a fairly high value resistor, so let me go back. I think I took that out fairly quickly. Oh yeah, so I'm soldering the resistor on right there, and it's a total mess because I'm like right in the middle of all that stuff. The chip whisperer was still running, but the device under test was turned off. Oh, was that? I guess that was a different value resistor. Oh yeah, this is the one I was trying to illustrate that was too high a value. So, yeah, that's interesting. So something else is still causing an amount of oscillation down here. I mean, that's clearly too high since I'm not even draining the gate of that MOSFET, so that's still effectively on the entire time. But these big edges here, I don't know where those are coming from. Well, I guess there's probably kind of a high current pulse coming from the MOSFET driver, like right when the edge happens, but then less sustained current. But still something causing this oscillation, still something causing this oscillation. Oh, for one question from the chat, why is the oscillation still bad if it still triggers an output difference? It isn't necessarily bad. It's only bad if it's something I can't control reproducibly. Because really the goal of this is to not just make any difference, but to make a very specific difference time and time again. So I need to really just kind of eliminate all the sources of non-determinism that I can. So anytime there's something that kind of randomly throws energy at the chip and sometimes causes it to break and sometimes not, isn't so great for me, unless I can like phase lock that energy to the the glitch signal that I'm sending out. All right, let's go back to our usual camera thing here. How usual is that? I think actually I need my other computer that has this design on it. But I can definitely get the cat camera back up and running. Oh, you're such a kitty. Okay, maybe I think I do want this screen. I just might turn off the DSLR and the scope. Okay. Cool. And laptop. Welcome to the party, Took. Hello, computer. Capacitors. Okay, cool. So this is what I was working on. I guess just for reference, I can open the previous version. Ooh, I even have the sound wired up here. That's amazing. It's still kind of... I'm still kind of used to video cables being just video. It's like a little weird that most video cables also carry audio these days. Alright, so this was the previous version of the schematic, which I kept a lot of stuff from. So you can see the kind of three-stage kind of totem pole-ish driver over here. So, whoa, zooming. Maybe I should have a real mouse for this part. I like KiCad, but it's much easier to use with a real mouse than with a touchpad. That is super little. Used to being able to like middle drag to pan. I don't even know if there's a way to emulate that on a laptop. Alright, maybe I'm stealing this mouse. Yay, it's mouse time. Mouse o'clock. There we go. So, this board had this little port over here with the 3 MOSFETs, some capacitors. These didn't all end up being 1 microfarad. I just kind of threw a bunch of footprints on there to make the board. And I had these jumpers for selecting whether the high voltage or the shorted glitching style was turned on. And then this was my circuit to both buffer the incoming glitch pulse and prevent it from getting stuck high. So if this input didn't actually go low, then this would end up forcing it there eventually. So the new circuit is basically the same thing. It just has some small changes. Okay, so onboard voltage regulators this time, since I decided to go with the 12 volts, and this seemed handy for giving me access to 5 volts for some other circuitry and 3.3 volts for this circuitry. So I just used what I had handy, which in this case was a 7805 in a TO20 packet, or TO22 pack, TO220 package. And this little microchip, what is this? MCP 1703 3.3 volt regulator. So this needs to supply hardly any current at all, but this needs to be a little beefier just because it's dropping a lot of voltage. Same high impedance input trigger circuit over here. One difference is I have all these little 3-pin footprints, which are where I'm mounting sockets for scope probes. I also have the glitch input footprinted out to both a 2-pin header, which is what I've got now, and a BNC connector, which is what I might want to be using soon. So more scope probes, more capacitor banks. Importantly, leaving space for resistors. I might actually only populate one of these and leave the other one shorted, but I left space for resistors in both places. So scope probes. So from a schematic point of view, it doesn't really look much different. It's just kind of stripped down a bit. If we go over to the PCB, it's somewhat more cleaned up. Nope, not that. This. All right. So this is my work in progress PCB design, which I'm going to finish up right now. Okay, so it's pretty compact. Right now everything is routed on the top layer. I think I'm going to go back and replace some of these traces with thicker traces, but it's still basically going to be routed like this. And this will leave the entire bottom layer for just an uninterrupted ground plane, which I think should also help. A lot of this routing is more straightforward. So these pins right here, this is where I'm going to be hooking this up to the device under test, I think with just a 2-pin header that goes straight down and onto the board. Or possibly a small length of heavy gauge magnet wire twisted together, which I think will give me a relatively low impedance wire, but give myself a few options there. And then several of these places for scope probes, for my little makeshift scope probe sockets to go in. Then I have a fairly straightforward path here. These two capacitors I wanted to be, these are also kind of new relative to the schematic. I think I ended up bodging those onto the current circuit. These are, I think, like 10 nanofarad and 0.1 microfarad caps, which those were for dealing with some of the high frequency oscillations that occur in the voltage, because of the voltage regulator not having enough capacitance with a good low impedance connection really close by. So, I have more capacitance that I can connect with the MOSFET, but regardless of that MOSFET circuit, I have these little capacitors just trying to kind of stabilize V-core a little bit regardless of whether the other capacitors are connected or not. So then this FET is actually doing the shorting glitches. It's got a nice short connection both for V-core and ground here, low area here, which is what I want. And then almost as high priority is the routing for this, this other MOSFET. And so for this, I have it connecting this lead to, this is another scope probe terminal where I can monitor the capacitor bank over here. And this is again arranged with the lowest capacitances here and then higher capacitances farther out. And then nice close by ground return for that, which also goes right back to the glitch connector here with low area. And then the inputs, so the gate for both of these MOSFETs go to their own scope probe, then a spot for a resistor, then a MOSFET driver chip with its own little bank of 12-volt capacitors. I should actually make sure I have enough that are rated for that voltage, but I suspect that'll be fine. So, and I think those are basically identical. This one is a little bit more space constrained, but basically the same. All right, I think that's pretty much it. And this is basically the same circuit for conditioning the input, but laid out differently so that it fits on one layer. So I think I need to add some new trace widths to KiCad. Let's see, where does that go? It's not here, is it? Oh, here we go. I think for the other, just in the interest of kind of keeping widths from changing unnecessarily, maybe I want to make my higher current tracks the same width as these pads. So that's 0.6 millimeters. I forget if this is the right place to be adding this in KiCad. Well, let's try it. Guess not. I think that was just for net classes. I don't think that actually helps. Oh, this is what I wanted. Yeah, okay, 0.6 millimeter tracks. I was using polygon fills for some of this stuff last time. I don't know if that was actually a good idea. I think it might have just given everything wildly variable impedance. But I'm still enough of a newbie at high-speed design to not have a good intuition for which factors are the most important at this point. Sometimes KiCad is really good at removing unnecessary tracks, but then sometimes it isn't. I'm also going to go ahead and do a ground zone both on the top and the bottom. So I'll have kind of ground, I guess they call this a coplanar waveguide when you have the signal and then ground on either side. But I mean, this isn't going to be anything controlled impedance or fancy. Just going to use these traces for a lot of things, I guess. I at least want to use them for the stuff around the MOSFETs and for power. I'll take this opportunity to kind of push things around if I want. Train. Oh, that fits there too. I think, I mean, I can use these tracks almost everywhere. The really thin pitch part here is just the buffer that I'm using for the input signal. Just kind of silly. But it was a nice fast part, and it was what I had handy, and it comes in an SC70 package. Yeah, that's a little bit serpentine, but it doesn't really matter because I've got plenty of local decoupling. Let's fix up some of these other long ones at least. This one's a little bit crazy, but I think I care a lot more about my ground plane than I do about this particular 3v3 veil. Frown. Go away. You're not invited anymore. that little stubby bit is getting in the way. Yeah. Let's see. Oh, I see. Got a sneaky little ground under the real ground. That warm, fuzzy feeling of the visual representation not matching the data model perfectly. This is going to be a little hairy to solder because I'm putting this jack on the top side. I'm going to have to leave a little space, but it'll be fine. Maybe it doesn't, I don't know why it didn't consider that a redundant track. It's supposed to remove redundant tracks when I'm routing. Same thing there. I guess I'm leaving a mess on some of these traces. Maybe it doesn't consider them to be the same if they have different thicknesses. That must be what's going on. Oops. Anyway, I'm going to stop fussing with this in just a sec and then add zones and get this ready to cut. This doesn't really need to be fussed over that much. Alright, it needs dimensions. No, maybe not. Let's see what that looks like with some zones on it. Cool. There's some room for improvement there. Did I tell that to do thermals? I don't actually want thermal reliefs. I don't really want to spend the room on them. Oh, haha, that's the option I wanted. That's better. Excuse me. Oh, I think the clearance is actually more than it needs to be. Like it's not really going to do me favors to have the zone clearance be higher than the global clearance, I think. Maybe slightly larger zone clearance. Cool. So DRC is good. Let's put a zone on the back, and then I think this is going to be fine. So that's just, the back's going to help us have a nicer ground. Ground here is much more important to me than some of these other traces that were running around the corner, so these should be fine. It's like a little tempting to make this particular part a little thicker. Because all the in and out here I don't think is going to be helpful. Where's this? One and a half, maybe? It's huge. What's that like? Yeah, okay. Maybe we'll play this game. I mean, as long as I keep the width consistent, I don't think it's going to cause weird, hard to debug signal issues. I am happier with that. So I guess I decided on 0.25 clearance for that zone. Next zone. Looking good. So the bottom is just ground, no tracks, lots of ground. Ground for the SMA, ground for the power, ground for all the scope probes, ground for the glitch board, or for the target. Cool. Let's make some Gerbers and go to the machine closet and make one of these. Alright, so we've got drill files, got Gerber files. That's all right here. We're just going to throw this on a USB stick, and then we can go to the closet. I'm going to get my wireless headset and catch up on chat real quick. Lots of discussion about KiCad. Alright, let's get the headset. Yeah, this could be exciting. I don't know if I've given this a proper test since redoing all my wiring. So theoretically you can hear me right now. I think that's working. Cool. Let's throw these files on a stick of some sort. Oh, and maybe I can get the wireless camera too, since that might actually work alright with the antenna it has currently. No files, just pixels. Alright, USB stick. Hi. Okay. I think I might even have something with... Oh. That still has... This is still set up assuming I'm walking around with an Android phone. Let's not do that. Let's put our analog video on here. Oh man. It is super weird how the first question when you're adding a new source in Open Broadcaster, it's like, what driver does it use? And then it gives you the name of all the sources. So I've got to remember like what kind of capture thing each is attached with. That's better. Oh, the touchpad on this thing is terrible. I think it's probably just picking up noise from anything I'm touching, like possibly even the microphone. Come on, mouse. Do I have to reboot my touchpad? That's somewhat better. Alright, I think that's what I was going for. Okay, so I think we've got the files we need. If I could eject this USB stick ever, someday it will unmount, and then I will be able to take it with me without leaving files behind. Someday. Man, why is it taking so long? Oh yeah, it's got the whole one or more programs might be trying to use it thing. Never mind which ones. Yay, ejected. I don't know why that took so long. Sorry about that. Let's go into the closet and let's bring the beer. Maybe I'll also bring the laptop just so that I can see whether things are going horribly wrong. Things that could go horribly wrong is dropping the laptop and the beer. Alright. Let's get this place comfortable. Now I've got to aim this camera on a delay. If all this shit works, I should be able to see, and the computer, and relatively word. Nice to yeah, let's get that out of the way. Okay. Had to check the screen to see if it was still streaming, but it was just this gray mass of hoodie as I rummaged around, so I think things are alright. Alright, homing. And I still got the bracket on there. Use about the USB stick, about to cut everything. Basically just decreasing this until the red areas go away. something weird about the, well, I guess the outline of the board ended up really close to the to these cuts somehow. Like that's, I don't really care about that. But I guess it's not going to let me. Oh, maybe that'll be fine. Maybe it will let me. Maybe it's just not letting me because the window's open. Let's see if I can go. Yeah. .09. So then we should see like nothing on the other side, just the isolation, but no tracks. So let's place this file not at the very left edge, perhaps. I like 3mm from each corner. And now the Z height is related to the tape thickness, but isn't, like, it's also kind of an opportunity to calibrate. Yeah, I guess before I was using a depth of .01, but let's just measure the tape again and maybe start at something conservative. Tape. All right, 80-degree engraving tool. Change the camera. You're getting bored of seeing the back of my head. Let's see what else we have available. Maybe, this is on such a long delay on the laptop. I'm gonna try just shaving off 0.05 millimeters. Or it's barely touching the copper. For all I know, the camera is I just saw the comments about the mic or the mic losing signals. I'm going to try putting fresh batteries in the mic because I realized I forgot to do that before this session. So that could be part of the problem. All right, fresh batteries in the mic. I don't know if that'll help, but the closet's also kind of far from the receiver. I'm also right next to this analog video camera, which no doubt is just doing radiation. Seems like it's good so far. I was just picking up with chat if you can hear my microphone at all and noticing the Oh, I wonder if this would help if I fiddled with the angle on the antennas way out here where the receiver for the mic is. I should also maybe put this up somewhere high instead of in this nest of wires where it's at right now. That could help. All right. I've made a possibly placebo change the angles of the antennas. Ferrite beads. So definitely no, I'm not sure. I figured I could probably add a ferrite bead and or a resistor on the gate of the other idea for bead then. Maybe I'll come out here and put the headphones on so I can actually hear what's going on with this mic. I mean, that's only going to help if I can reproduce it out here. So if I'm talking out here, seems fine, but I'm also really close to the receiver. Oh man, Tuco is super cute out here too. Hey, buddy. I just gave Tuco a very tiny static shock when I touched his nose, and it was cute, but I don't think he liked it. Well, I might just have to find a better place to put that microphone receiver. I mean, it's working out here, but I'm also standing maybe 5 feet from the receiver because the earphone wire is also not super long. Can still kind of hear the milling machine through the headset. Tuco, what do you want, little cat? That's what I thought. So yeah, I don't know how much of the conversation came through in about what I was doing setting up the milling, but oh man, maybe I should take off the headphones. There's a tiny bit of delay on the headphones, and it's I think at that point where it makes it kind of hard to speak. Yeah, a small bit of audio processing delay. So yeah, my current strategy for doing these kind of high density but otherwise not especially fiddly boards is to use the 80-degree mill and kind of slowly step it down until I'm cutting consistently through the copper, but otherwise try to keep the touch pretty light. And then I'll go back through with an end mill to do the holes and the perimeter. So it's usually just 2 tools per side. And usually, since it doesn't matter what order you do the holes versus the perimeter, usually I can... Usually what I would do is, like drill or, do the traces first, and then and then I would like mill the holes from one side, then flip it over, mill the holes from the other side so that I get a clean finish on both sides without having to have sacrificial material underneath. And then do another tool change to go back to cutting traces. And then the last tool change is just for cutting the edges. So... Hey, Tuco. Well, I'm going to go back into the closet. I hope some of the audio comes through. I also maybe wonder if putting the transmitter in like my back pocket instead of right next to the cell phone would help. Things could make a difference. Ooh, this transmitter sure does have the warmness to it. That is the stuff. That's the stuff right there. This is the stuff. Check that, if that is going to focus at all. But that's what we got. Pretty happy with that. So yeah, I'm gonna do the tool change to, well, let's see what we need to cut the holes. Usually I use a 1/64 inch. I think that'll work for this, but let's just check that out. Oh. This is the wrong drill file. This is the drill for non-plated through holes, which is not what I want. Let's fix that. Can I change the files here without totally re-importing it? Maybe not. Okay, well that was at 3 and 3 with a trace depth of 0.09. Okay, so this was the problem. This is not supposed to be the NPTH, which I didn't really pay attention to before, means non-plated through holes, which is not my normal drill file. That's like just going to have the hole for the voltage regulator, which I don't really care about. So let's have that drill file instead. That's also not a good sign, but let's see if it loaded anyway. Really? Interesting. That's not so good. Yeah. $166, huh? I guess this must just be in the wrong format. But the drill for the non-plated hole looked fine. Brrr. Oh. Back to Kai. Hey, cat. Well, I think this might have been just a problem with exporting the drill file. Let's take another look at what we have. Hey, cat. You sure are a kitty. What do you mean by that? I don't know what a matrix 8x8 is, but that sounds more impressive than what this is actually connected to. Hey, Tuke. I think Tuco wants something to eat. Okay. So, I just want to mess with the drills, because the traces are fine. So, I want that. Maybe this was also just in a format that... Because if I forgot to change this to Gerber format, then maybe they tried to parse it and it just didn't really work out. I think I want inches. I think I want decimal. Let's try that again. Hey, Chico, I hear you, buddy, but I'm in the middle of a thing. Alright. Bonk. Hello, USB stick. Oh, Tuco is so cute and yawning. Okay, hopefully it was just that, and I just needed to... I think I just messed something up during the export. Yeah? Tuco just orbits the camera. Okay. Is that done copying? Can I eject this and go back into the closet? Other than its apparent function as a Faraday cage, it's a pretty nice place to hang out. There might be something to that. I have a hard time getting Wi-Fi in that closet too. It's part of why most of the equipment in there is on the wired internet. Or the ether web. Alright. I hear you, Tuco. Oh no, I accidentally threw it in the trash. I would wish you good luck in finding it, although I'm not really sure I want you to at this point. Alright, anyway, I'll let Tuco figure out what he wants to do with that particular challenge. I'm sure there are other bolts if he'd rather. So, copy this to the desktop again. Okay, can we load it this time? Tuco's outside. I like letting Tuco hang out in this closet sometimes when I'm here, but I have to keep a close eye on him because he gets into trouble easily. Oh, bottom. This is the slowest computer. Alright, does that help? Really? And that is the new file. Can we check out line 238? Oh, are there no line numbers in this editor? What a bad editor. Anyway, I think it was something like one of these last few. Are these just missing carriage returns? I'm not quite sure what it's trying to do here because I don't know what this format is about. I don't know what a G85 does. Oh, it's a slot. It's a slot. It's a slot. Oh, it's the DC jack pinout. Oh, can I just remove these? Or turn them into something I can deal with. So these, choose a size and then a location. Like it's a tool change and then a location. So I guess this is a tool change, a location, and then a move or something like that. So I'm just going to edit this by hand and we'll see how this works out. Let's try that. I mean, it would be great if it supported this though, because this mill can clearly cut slots, and it would be like, I was kind of hoping that I would get a slot in this case, so. Oh well, I mean, it doesn't matter if I have to kind of bodge this connector slightly. Let's see if this works. I wonder if this is at all in sync, like if you can see me talking and if it's all in sync. I would expect it to be, but I don't currently have a way to verify it. So I'm just going to load this in again and see if my hack to the Gerber file actually fixed anything. Yay, okay, cool. So placement, I need to fix this to, oh, this was at 3 millimeters before. Oh, okay. Let's double check that distance. It wants me to put the window back on. All of these holes are pretty wide. None of them are vias. A couple of them are for 0.1-inch headers. Some of them are for these scope, or well, they're for like female machined pins, which I'm going to use for scope probes. Change. Nothing like a tool change. Here's the 1/32. No, that's the 1/16. This is the 32nd. This should probably be pretty quick, actually. You know, I'm actually not going to cut all the way through here. I'm going to because I'm still going to need the 1/32 inch tool to cut the outlines after I do the next traces, so I think I would get better edges if I'm going to set this to a Z height slightly higher than this, maybe 0.36 millimeters. Oh, and I don't want to cut the outline yet, I just want to cut the holes. Okay. That's better. So these should cut not quite all the way through. Didn't I already do that? Oh, right, I canceled it in the middle of the tool change. Now, I would definitely expect the mill to lag relative to the wireless, because the mill's on like a little Linux box capturing JPEGs. definitely of my modified slots where it just went very first. This over. Let's maybe dust this off slightly. I will turn off my mic. Alright, I think we're back. Oh, gotta flip this over. Alright, that's this down. So, bottom side, one. So this, I'm going to go back to the Z height we had before, or even a little less actually, because I don't mind if these are cut a little bit thick, because they're just isolation rings. So maybe go all the way down to 0.1, and then trace this holes and outline with a combination of the 1/32 inch tool and the 80-degree tool. Right. the outline. I should put a little bit of tape to hold. Doesn't go flying. I don't know, is my camera battery dying? Looks like it is. Unplug to save you from the static. And replace. I'll put the battery in this camera before doing the tool change. Oh, Tuco's waiting out here for me. Hey, Tuco. I wonder what Tuco thinks about AA batteries. I mean, I'm pretty happy he doesn't think they're tasty. Times like this, I'm glad I have so much AA battery charging capacity in my lab. This camera, the way it's set up right now, runs on 6 AA's. It might be slightly easier to use a LiPo pack, but I had a bunch of these and they seemed a little bit safer to just like randomly throw around. Three batteries. Oh, I need 2 more. I have to get some from this other bin. Battery land. How's that? Do we have power? Looks like we have no file, but plenty of power. What's up, cat? I hear you. Let's go do some more milling. All right. 6 AA batteries. We shall continue this. He can totally get it. But he's smart. What's up, cat? Just noticing some of the chat about video, getting some Cat 5 for video into this closet, but I'd still like to have a wireless camera for stuff that isn't already. I've been thinking about video for this. I don't know. I'd like a camera that can follow my cat around, ideally hanging from the ceiling, but possibly, you know, it could be a stationary pan tilt zoom, or it could be something. I'm thinking about video solutions for that. I heard from Ken Keeter. We can do that. Having wired video in here is only part of the story. I would also need to figure out an audio. So I think maybe the closet. It's weird. Kind of smells like cheap furniture. Alright, I think that's turned on. Alright, scrap piece. And our nice little board. Great. I think we can end today's closet experience. So I've got the board, the laptop, and the USB stick, and the camera back outside, where there is cat, audio, and beer. Hey, you're just hanging out right there. What's up? You guarding the fancy plastic? Ow. What's up, Tuco? Oh, let's go here. Hey, Tuke. Wow, my cat really wants attention. That's something new. Hey, buddy. Alright, I think we can be done with the wireless mic for the moment. What's up, cat? Oh, can we still somewhat hear this? Yeah, that seems alright. Hey, Tuke. Tuco? Oh, you're such a cat. So, got our circuit board. Let me just sand the edges a little bit because it's kind of a little bit sharp right now. Tuco, what do you want? The usual bolt-based entertainment. Tuco's got his bolts. Where did I leave my beer? Oh, I guess my beer was in the closet. I just forgot about it. See, this is why beer and machining don't mix. The machines will make you forget about the beer. I don't even know where to put the cat camera because the cat certainly doesn't stay in put. Alright, so here's our thing. Is that focusing? Alright. So straight off the mill, that's the top side, that's the bottom side. Just gonna clean up these edges a bit. I think this was partially because I didn't actually go all the way down on the outline pass, which was a bit of an oversight, but not enough for me to actually go and correct it after I'd already started it. And then also I think my 32nd inch tool is getting a bit dull, so I should probably replace that. Give these edges a bit, or corners a bit of a rounding, and also just sand the faces a little bit just to get burrs off the middle of the board. Also try not to have conductive debris every single place, but nice tarnish-free surface, and not very many burrs left. Yeah, seems pretty good. Nice and tidy. Let's get this chucked up in a vise. Start putting things in it. Do I need to throw some things for you, Tuco? Is that the state of things? The battery on the laptop is low. find it, little cat? Little tiger looking for bolts in the hammock, just as you do. Well, so my strategy for these scope probes. So you saw my previous prototype over here. I had these kind of terribly precarious looking turned pins that I extracted from IC sockets. So I'm going to be doing basically the same thing over here, but pushing them into the board instead of having it be precarious. So I've got these little fragments that I plan to fragment even more. So I was hoping these would press fit. They might be slightly too big for that. Alright, they might have to sit on top. I was super lazy about the footprints for these because I didn't really want to spend a bunch of time designing a board that would just be another iteration in this experiment. And I care most about the inner and outer holes here. The middle one I left in to be, just in case I needed it, but it was also just kind of an artifact of reusing a footprint. It'd be really nice to have a little bit bigger hole there. But let's see how well those things surface mount. Oh, that beep was the soldering iron telling me it has some warmness to offer. So unfortunately with these not press fitting into the holes, they will be a little harder to keep straight, but I should still be able to solder them on both sides and have them be relatively sturdy. Seems fine. Oh, can we focus? Those don't look amazingly straight from that camera angle, and they aren't like really straight, but they're straighter than they look. It does at least have that nice property that once the solder gets all nice and surface tensiony, it pulls the pin into a relatively good position. So let's see how these look on the back, just while we're doing the first couple. Yeah, so they're not amazingly straight. But there's the back. Just have mechanical anchoring there. I'm hoping these won't fall out. Man, I don't know. This would have been working a little better if it had gone according to the original plan, where these actually push all the way through. Yeah. The pin on this side is just so much smaller than the hole that it's having a hard time creating a nice solder fillet. I'm going to see if I have just some little drills I could open these holes up slightly with. Where do I have tweezers? How about these? Looking for some solder braid to take off this excess. There's some little solder braid over there. I've got a better spool for this. I've got this really thin stuff I could use. This is a little thinner than I actually would usually use for this, but it's what I have handy. lots of solder and heat and flux. Cool. Let's drill that a little. I think all my regular drill bits might be too big. And this one is 1/16 inch. And it might be a little bit too big. I'm going to try drilling at least part way through just to see if that helps it sit. I suppose a pin vise would be really useful for this, but I'm kind of lazy about it. Yeah, so I just like partially drilled through the top with a 1/16 inch, and that seats slightly better. Well, at this point, I might just actually revise the footprint and the design slightly. Since now there's this problem plus the slots, and this would be a little easier if I just went and made the footprint a little bit less narrow. I mean, I could just have it stick up, but I don't know. I'm also feeling like I need a bit of a break from streaming at the moment, so maybe I will take my break from this and then figure out how I want to proceed and either modify the files and cut a new board or just proceed with this one. Since, I don't know, it's kind of balancing two things that are each likely to be annoying. Because if you look at how the slots came out over here, I mean, you know, I can work with this. I was planning on, when I edited the G-code, just like surface mounting the jack above the footprint, just kind of not worrying about the holes, or going in with a drill press and manually widening them. But that's annoying. And I might just fix the footprints and then cut another board, since it doesn't take that long to cut another board. But on the bright side, this new soldering iron is pretty baller. This is my first experience with the Heiko FX951, and it's just really amazing how quickly this will heat up these big copper planes and just keep them hot, and so that's been really nice. But I think I'm going to take a break from the streaming and hang out with Tuco and figure out what to do about the rest of this project. Hey Tuco, what do you want? He's meowing over by the front door like he wants to go out into the hallway, but I can't quite tell. Alright, I guess I will have to go over there and figure out what he wants. So, thanks for tuning in, everyone. I appreciate all the help and support I've been getting from everyone. Super big thanks to all my patrons and everybody who's been donating equipment and time, and you know, it's nice to hear when people are out there. And I am also open, if you have suggestions about stuff that you'd like to see, stuff that's working, stuff that's not working, I'd love to hear all of it. So leave your suggestions in the comments or hit me up on the Twitters. But until then, oh, there's Twitter, or there's Tuco. Tuco, do you want to play Bolt a little bit before I go? Meow. Do you want to play Bolt, Tuco? Good job, little guy. Good tiger. You're such a good cat. Oh, focus. Focus, little cat. I'm also just thinking I'm kind of unhappy with how large this board is. And it's probably not a big deal, but it's like a trade-off. Making it larger might make it easier to put together, but it also might make it get in the way more when I'm actually working on using this board. So I've tried to, at least in this design, keep, over here I've got the input. So there's an SMA and or 0.1 inch header for the trigger input. There's power input. Some of these other power signals I'll end up connecting to the device under test. And then this thing is what actually goes to the vCore on the device under test. Then the rest of this is like oscilloscope probe stuff that I want to be accessible, but doesn't really need to be in a particular place. Oh, Tuco's so relaxed and blurry. All right, Tuke. Good job, little dude. All right, happy hacking, everyone. Until next time. One more bolt for the road. All right. All right, thanks for tuning in, everyone.